All right, so this video is to talk about the central limit theorem. But before I start talking about the central limit theorem, I want to kind of recap some notation so that kind of we know what we're talking about as we move through the central limit theorem. So starting with, we need to make sure that we understand what is the difference between a population and a sample, and how do we represent the size, the mean, and the standard deviation for each of these. So when we talk about the size of a population, we always use capital N. When we talk about the mean for a population, we use this sign, this Greek letter mu. When we talk about the standard deviation of the population, we refer to, or we use the sigma notation, the Greek letter sigma. Once we move on to the sample, we use lowercase n to talk about the size of that sample that we are collecting out from capital N, which is the population. We talk about X bar to refer to the mean of that group sample that we are taking out from the population. And we use S to refer to the sample size of the population. Now, remember again, and this goes back to the starting of any intro to stat class, we always talk about having a population, and I'm just going to refer to as a big rectangle, and we have population of size n with a mean of mu and a standard deviation of sigma. And then from there, we collect a sample, and that sample has size n, has a mean of X bar, and has a standard deviation of S. All right, when we move on to the inference part of the course, which is what is coming after we learn about the central limit theorem, we need to understand what is the difference about the population and the sample, and how are we collecting the samples to calculate the standard deviation and the means. But also, in reality, we always work with samples out of population because it's very hard, time-consuming, very expensive to collect data from whole population. So we always rely on samples to make inference about our populations. Now, the thing is that we don't always know the mean and the standard deviation of that population. So we will always need to estimate the mean and the standard deviation of the population using some information from the sample, right? And so here is where the central limit theorem comes into the game. So I'm going to say central limit theorem as CLT as we move forward. So the central limit theorem pretty much says, and I'm going to kind of look for like a definition, but it's pretty much it's a theorem. So it's something kind of given to us. So the theorem says that no matter the shape of the distribution that we start with, when we do resampling, the distribution of sample means it's always normal, all right? So then how do let me just find, so let's see. All right, so I'm trying to find this same definition that you will have in Newton, but I don't see it. So it's pretty much, it says the central limit theorem, it's a theory. claims that the distribution of sample means, and I'll explain that in a minute, calculated from resampling will tend, that's a D, will tend and to normal as the size of the sample increases regardless of the shape of the population distribution. All right, so this is what the theorem pretty much is saying. The theorem says that we are talking about two distributions, and that's something that you really need to understand. We are talking about the distribution of the population, but we are also talking about the distribution of sample means. All right, so we need to talk about those two and understand what difference between them is. So we have a population that has a distribution, all right? That distribution can be uniform, it can be skewed to the right, it can be skewed to the left, it can be normal, it doesn't really matter. So I'm just going to do something here, and I'll say that the distribution of the population is skewed to the right. All right, remember that being skewed to the right means that as you have your data points, this is the behavior that you observe from your population. So all the data is underneath this curve, and this is the shape that it has, right? And so I'm going to try to be fast in here, but this is kind of what the observation is. Sorry for the lines, I'm just trying to be fast. All right, so then again, all of this green dots, it's a data point from your random variable X that you want to understand, right? So we have a random variable X that is skewed to the right. All right, so what are we going to do with this? What we're going to do is we are going to create a new distribution. So new distribution with the means from the samples. And here is kind of what you need to understand what we're doing. So let's just go back to the population. So we are going to collect samples of the same size, and we're going to do many of them. All right. So let's say that we are going to collect samples of size 25. And we are going to collect a total of 100 samples. All right, so we are doing 100 samples, each of size 25. So then I'm going here and I'm not going to do all of them, but this is what we do. Let's talk about sample one. So we collect a sample of size 25, right, out from our population. Once we collect that sample of size 25, we are going to calculate the mean for that sample. In other words, the sample mean. All right. So once we have that, I am going to call this measure that we're getting from here X bar 1. So it's the mean, it's the sample mean for sample number 1. So we can kind of pair them one with another. All right. I'm going to do that again. So I'm collecting a second sample. So again, I'm going to collect a sample of size 25. And I'm going to calculate the mean for that sample again. I'm going to calculate the sample mean, right? And here you see how I'm using the same language as in here, sample means. And so then I'll do the same. And once I'm done, this is going to be X bar 2. All right, I'm going to keep doing this many times. All right. And so at the end, I'll just continue. And I'll do this 100 times. So when I collect the sample number 100, again, I'm going to do exactly the same. I'm going to collect a sample of size 25. This is a sample number 100 because I have done it 100 times. Again, vocabulary here, we are talking about the sample mean. And so again, when I do the same, this is going to be my sample mean number 100. So I have 100 observations that are actually means, averages that I calculated from the samples. So all those X bar 1, X bar 2, X bar 3, all the way to X bar 100 are going to create a new distribution, which is the distribution of the sample means. So when we talk about the distribution of the sample means, we are talking about distribution like this. All right. And so what the central limit theorem says is that this distribution, it's always normal, no matter the distribution of our population. So then we know that a normal distribution is going to look like this. Let me fix that. Do it a little better. All right. I don't have any scale in here, so I'll just try to do my best. That doesn't look very normal, but I'll try it again. It is hard to do it in the iPad and with the Apple Pen. Kind of like that. That's better than before. So I'll just leave it like that. Let me see if I can. There we go. All right. And so again, remember that what you have in here is 100 points. And each of the points represents a sample that you collected of size 25. And the dot represent the mean for that sample that you selected. All right, so this is what the central limit theorem says. The bigger the sample size, and the bigger the sample size is, the more normal your distribution of sample means will be. All right, so then what else does the limit of central theorem says? It says that if you have a distribution, right, and you know that you have a population with a mean mu and a standard deviation sigma, all right, again, those are the letters that we use for population, mu and sigma, all right, so if we know that, then we know that the distribution for the sample means, which is this one in here. So this, let me just move this down. So the distribution for the sample means distribution of sample means, then we know that this distribution is normal, and we know that it has a a mean of X bar and a standard deviation of sigma over the square root of n. Right? And we know sigma because that is the standard deviation of the population. And then X bar, it's the same as mu. So the mean for the distribution of sample mean is going to be the same or very close to the mean of the population, but the standard deviations are going to be different. So once we know the standard deviation of the population being sigma, the standard deviation for the distribution of sample means is going to be the standard deviation of the population over the square root of the sample size. So in the example that I'm using here, sample size will be 25, right? Not the number of samples that I'm taking, but the size of the sample that I am using. All right. So from here, I can show you, and I'll show you here real quick, what do we mean by this? So this is a simulator. So if I start with something that is skew right? So I have a distribution here simulated with a mean of 102.04 and a standard deviation of 97.67. Okay, again, this is just a makeup, like a distribution that has been made of with those numbers. So if I do the sampling with samples of size 2, this is what we get. So this in here, this craziness that you see here is the standard, this distribution for the sample means. So again, collect a sample of size 2, calculate the mean, put it down here. Do it again, put it down here. Do it again, put it down here. It's doing this 20,000 times, all right? If I increase the sample size to n, so I'm doing 20,000 samples of size 9. So you see how it got better, a little better in terms of being normal. If I increase to 25, so now I am taking 10,000 samples of size 25. You see how normal it's getting. And you see how this mean is approaching the 102.04. So if I go back, this is 103.14. This is 101.92. When I go to n equals 25, 109.97. If I go to 100, so I'm collecting 2,500 samples of size 100 each. I have a sample. The mean for the distribution of sample means is 101.84. And this X bar, this in here is the standard deviation for the distribution of the means. That is why you have that X bar down here. All right. So that's what it says. If I go back and I do a skew left. All right. So again, if I do 100, here we have that normal curve. The mean for the distribution of sample means it's very much the same. The standard deviation is 9.72. Again, this in here, it's coming from 97.67 divided by square root of 100, which is 10. So that's 9.76, 9.72. So again, it's an approximation, but that's what you have. Same thing if you have a normal and you collect samples of 100. Same thing will happen. From the normal, we go to normal. And that is the work of the central limit theorem behind the scenes. All right.